Okay, welcome back. So I left you with this little problem to have a look at. So what temperature black body would give a peak of emission at the wavelength corresponding to this energy of 3.4 electron volts? So the energy required to ionize hydrogen from the n=2 level up to the continuum. So just three steps involved here. So let's take this energy of 3.4 electron volts. So you'd need to have to look up how to convert that to SI units first, to joules. The electron volt comes from the amount of energy that's obviously required to accelerate one electron through 1 volt, and that just corresponds actually to the charge on the electron. Okay. So that's where that number 1.6 × 10⁻⁹ comes from. That's actually the charge of electron in coulombs. Okay. So just to convert from electron volts to joules, you multiply by this number here, the charge on the electron. Okay. And that will give us that number there, 5.4 × 10⁻⁹ joules. So I mentioned a couple of times hopefully you're familiar with this idea. So this is the idea of how much energy is in a photon with a particular frequency or wavelength. Okay, so I'm using nu here as a symbol for frequency. You'll see that throughout astrophysics, really, well, physics as well, to be honest. You may well have used hf before, but I'm going to use h nu. Okay. So this is energy of a photon with a particular frequency, just multiplied by Planck's constant. But here we're dealing with wavelengths, so we can convert between frequency and wavelength just through this, the normal formula for electromagnetic radiation to convert frequencies to wavelengths, which is just that nu is just c over lambda. C is the speed of light, and lambda is the wavelength. Okay. So put all that together. Lambda is just hc over this energy. And so here's h, Planck's constant, speed of light. This is our energy. So if you put all that in, you basically come up with a wavelength of 360 nanometers. Okay, and then just apply our Wien's displacement law again. Here's the constant 3 × 10⁻³ on the top, and here's our wavelength in meters on the bottom, and that gives us about 8,000 Kelvin. Okay. So that's telling us if you had gas with 8,000 Kelvin and the radiation from that, if everything's in equilibrium, would start to ionize hydrogen atoms from the n=2 level. Okay, and this kind of number we'll come back in a moment. Okay, so next we want to get into what it is that is going to determine how strong an absorption line is. So what do I mean by absorption line strength here? So you saw those sort of black lines superimposed on the continuum spectra earlier. So basically, the strength of an absorption line, if you plot it as a spectrum, as we'll see later, you've got a little dip in the spectrum. So it's really the area of that dip in the spectrum is what we mean by absorption line strength. So the stronger the line, the deeper and deeper and deeper, the blacker and blacker it gets. Okay, so that's what we mean by strength. So there's a couple of things here that we need to worry about. Well, only really one that we're going to worry about. So the first part of determining how strong an absorption line is really just depends on atomic physics. So obviously what we're talking about here is the interaction of a photon coming along and interacting with an electron exciting. So that is an electromagnetic interaction between the electromagnetic wave and a charged particle. And the probability that the photon will be destroyed and absorbed by the electron, that's all to do with atomic physics, quantum physics, basically. So that will just be determined by the particular electronic transition that the electron will undergo. So here we're talking about using the H alpha as an example. So there is a particular probability associated with a photon coming along with that particular energy in terms of it being exciting the electron up to the n=3 level. So that's just all set by atomic physics. For any particular transition, it's a constant. Okay. There are lots of different ways you will see in physics that is described. So strength of transition. You might also see mention of absorption cross sections. You can think of that in various different ways, but that's not really concerning us here, to be honest. What's concerning us more is this second part. Okay, so you can't have a H-alpha absorption line if you did not start with hydrogen atom in the n=2 level. Okay, so how strong the H-alpha line will be depends on how many particles you've got in that, how many hydrogen particles you've got, how many hydrogen atoms you've got in that n=2 state. So for absorption lines, everything depends on the population of the lower state of the transition. So you go from a lower state to an upper state. Everything depends on that starting point. How many electrons are in that lower state ready to go. So you can see that is going to depend on different things. Okay. Obviously, you need some hydrogen in order to give you a Balmer line. Okay. If you haven't got any hydrogen, you haven't got any Balmer lines. So it depends on the abundance of the element. We're going to look at the idea of temperature in a moment. So definitely depends on temperature. Okay. Because which level the electron is in the hydrogen atom depends primarily on the temperature. There is also a dependence on the density. If you make things more dense, then it can have an effect on the state of the gas as well. But given that, well, we haven't talked about this much yet, but basically if you go from star to star to star, the abundance of the elements does not change drastically, at least not usually. So if we take the abundance as given, and for most stars are mostly made of hydrogen anyway, if we use hydrogen as the example, the density dependence is not strong, so temperature is the one we're going to look at. Okay, so here's a fundamental piece of physics. Okay, if you ask yourself for a given atom, so we're discussing the hydrogen atom here as the simplest example, how do you know where you are likely to find the electron? And don't forget that quantum physics is all about probability rather than certainty. So there's a certain probability of finding the electron in a particular level at any particular time. So that distribution of population, so if you've got a whole bunch of hydrogen atoms, they're not all going to have electrons in a particular level. There'll be a distribution, but there'll be a well-defined probability associated with that. And that depends on temperature. Okay. So basically, if you start heating up an atom or an ion, you are more likely to excite the electron up to higher and higher energy levels within that. Okay. So that process is referred to as excitation. Okay. So as if you take a set of hydrogen atoms, and if you increase their temperature, the chances are you are more likely to find electrons at the higher levels rather than down in the ground state of n=1. So as you increase the temperature, more and more electrons will hop up and stay in the n=2 level for a while. Okay. So that process of increasing the temperature and getting the electrons up to a higher level, you would say the atom is in an excited state. It's more it's excited above the ground state, the n=1 state. So next thing to ask ourselves is what happens if you keep on heating it? Okay. So you're going to get electrons going up to higher and higher levels, 3, 4, 5, 6, all the way up. Okay. What happens if you heat it too much? Okay. your electron is in danger then of being removed entirely from the atom. Okay. And so that would lead to the process of ionization. We discussed it briefly before. So if you heat it up too much, you're going to basically destroy your atom by removing the electron entirely. So the electron will be liberated from the atom and just leave behind, in the case of hydrogen, just leave behind the proton. Okay. So that process is referred to as ionization. Okay. Now, hydrogen is a bit of a boring example because all you do is, you can only ionize hydrogen once because you've only got one electron. So here I'm using the example of helium, the next most complicated element. Obviously, neutral helium, as I've indicated here, with helium-0. So just the helium atom obviously has 2 electrons. But if you remove an electron from that, then you end up with singly ionized helium. Okay. So that still has 1 electron. So it still has the potential, still has an electron in a whole load of energy levels. So it will still produce spectral lines. Okay. And we'll come back to this a bit later. So again, a little bit of notation here. So this, the sort of your traditional physicist would always use this notation. So you've got the helium atom, which is neutral, or singly ionized helium, which is helium plus. Obviously, you can have doubly ionized helium, in which case you've just got the helium nucleus, but let's just stick to this. But again, using the spectroscopic notation that I mentioned earlier, then the helium atom, lines from the helium atom would be described as helium-1 lines. And again, this is a Roman 1. Lines from singly ionized helium would be described as coming from the Helium-2 Ion. Okay, so this is a Roman 2. So this notation will come back again in the module later, which is kind of why I'm introducing it now. Don't need to get too hung up on the details here now. Okay, so bearing that kind of general idea in mind, an absorption line for a particular species now, so we might focus on the hydrogen atom, will have a maximum strength at a particular temperature. Okay, so if you think about at low temperatures, then most of the species will just be, the electrons will mostly be sitting around in the ground state. Okay, they haven't got enough energy to get up to the higher levels. But as you heat them up, and if you heat them up a lot, then at very high temperatures, then that species will just become ionized up to whatever the next ionization stage is for that species. So that means there's a particular temperature that is the sweet spot, if you like, for a particular spectral line. Now, this is a complicated little looking diagram. I want you to just follow along with me and just focus on one particular curve here to start with, the one labeled H. Okay, and let's focus on the top scale here rather than the bottom one. So this is a temperature scale that we've got here. And we've got, it's a schematic diagram really. So this is just a graph of line strength against temperature. The temperature is going backwards. That will be revealed a bit later. But basically, let's focus on this curve labeled H here, which is basically the strength of the hydrogen lines. H alpha or H beta, the whole Balmer series, the Balmer series of hydrogen lines. Okay. So this curve puts into action the words that we just talked about. So at low temperatures, so down here, okay, the hydrogen atom, the electron in the hydrogen atom will be mostly found in the ground state, in the n=1 state, and there will be very few electrons in the n=2 state, because the gas is literally just too cold to excite it many electrons up to the n=2 level. As we get further and further up in temperature, the hydrogen atom will get more and more excited, and so you're going to find more and more electrons popping up to the higher levels. So the chances of finding an electron at n equals 2 level increases rapidly here. So you can see it rapidly going up with temperature as we go up through here. But around about this sort of temperature here, we reach a peak. So that's what I mean by there is a particular temperature at which the strength of a particular line will peak, but it then starts to go down again. Okay? But that's because we've reached a temperature around about 10,000 Kelvin here. And around about that temperature, that is when the hydrogen will start to be ionized. You're heating it beyond the point at which the excitation is the dominant process. After this, after 10,000 Kelvin, the dominant process is you're just literally ionizing a lot of the hydrogen. And so basically the abundance of the atomic hydrogen that you need is going down. Okay? And so here, atomic hydrogen is being turned into ionized hydrogen, so just a free proton basically, which does not have a set of lines at all because it hasn't got a bound electron. But basically, you know, your n equals 2 population is decreasing here. And so that is why it decreases again. So it increases initially with temperature due to excitation, but then it starts to decrease rapidly because of ionization. Okay? And so that's why the Balmer series of lines in the spectra of stars will peak around about a temperature of 10,000 Kelvin. The problem I left you with just at the break, you know, we found that even at 8,000 Kelvin, then you know you will start to ionize directly out of the n equals 2 level. Okay. As we go further up here, you don't need to go much further before you're just starting to ionize with all the hydrogen, regardless of which level it's in. Okay. So the next one I want to draw your attention to is the helium sequence over here. So here, the helium lines, they require a lot more energy to get them going to start with. Okay, we'll come back to a problem like that later in the lecture. So you need to excite them here. So this is the excitation going up. But again, here you reach the peak, this time at around about 25,000. And then you will start to ionize your neutral helium, your atomic helium. But of course, here you've got 2 electrons now. And so next, as soon as the lines from atomic helium start to decrease, the lines from ionized helium in the optical spectrum, helium-2, start to come up. Okay. So you get a sequence here. Here's the helium-1 sequence, and then if you go up in temperature, you start to get the helium-2 sequence peaking up. Okay. And the same is true for all sorts of things. Okay. So you've got whole sequences here. So there's 3 different ions of silicon here giving rise. Okay, so there's silicon-2, silicon-3, silicon-4. Okay. So that each of them will have a particular temperature at which the strength of their lines peak. Okay. Now, I mentioned before that hydrogen is the most abundant element in the star. But you can see lines due to other elements here, even metals like calcium, iron, magnesium, silicon. It doesn't mean that these stars have a huge abundance of calcium. It just means that the probability of a photon giving rise to these lines in the calcium-2 ion is very, very high. So the atomic physics part is very strong. So that these lines are strong because they have a high probability of absorbing photons, not because they are particularly abundant. Okay. So the strongest lines in an optical spectrum does not immediately tell you what the star is made of. Okay. So that's why you have to understand the temperature first, and the density, and all the atomic physics before you can decode all of those lines in order to give you abundance. Okay, but the bottom line here, the main point is that the strength of the spectral line primarily depends on temperature. So this therefore gives us a way of determining the temperature just by observing the spectrum of the star. Okay, so if you've got a set of lines with particular strengths, okay, that pattern is going to tell you the temperature of your star. Okay? And it's that gives rise to this strange notation on the bottom here, which is what we'll go on to discuss next. But let's leave you with a little thing to work out. Well, not really work out. Have a look at. Okay. Have a think about. Okay. So I just showed you that graph. Okay, where you could see that the helium-2 lines required much higher temperatures to form their lines than the hydrogen lines from the Balmer series. Now, if you think about the helium-2 ion, it's basically instead of a proton in the center with a single electron around it, it's actually a doubly charged nucleus with a single electron around it. You've removed one of the electrons from the helium atom, that just leaves you one. So this is referred to as a hydrogen-like ion. So it's still got a single electron, just like the hydrogen atom, but it's got a different charge on the nucleus. And for those of you who've looked at sort of the idea of the Bohr atom model of for hydrogen, you come up with this idea that the energy levels are proportional to sort of 1 over n squared, where n is the atomic level number, the quantum number. So the n that we discussed earlier, n equals 1, n equals 2, etc. But then you've got Z being the atomic number, so the number of protons in the nucleus. So again, just have a little think about that. So what are the implications for this, for the helium-2 sort of energy level diagram? And why does that explain why we need higher temperatures for the helium to get the helium-2 lines extended? Okay, have a think about that and come back.